kind of what we're stuck with from that. And you don't have to necessarily read that in detail. That's just where we left off last time. We have one more concept for talking about the integrated way that metabolism works, and it's a subcategory of how mitochondria, so oxidative metabolism, how that fuel mix changes. And it's a very small area. It's almost like a little cul-de-sac here at the very end. I want to mention I have office hour today for 90 minutes after class. I'll stay till noon if that makes your life better. I posted the podcast from Thursday. Sorry it wasn't up for the weekend, but I didn't find it on my that until this morning. And otherwise, I think we're kind of caught up. A few of you were sick for the midterm. I can tell you showed up and were visibly ill and hacking through the midterm and did poorly. I'm going to give you a chance at some remedial work. This is only people who either notified me beforehand or were visibly hacking up furballs during the exam. I need evidence in order to offer remediation. All right, so this is what we've already talked about everything. Eliza, that slide right there before, this is what you summarized in your email to me, basically, from your weekend studying, and it was correct. This is a last little area to talk about before we move on to new topics, which I think you'll enjoy quite a bit. Again, sorry about the color. It kind of makes it harder to... I wonder if I drop this down if it helps. Oh, yeah, let's do well. That's a little better. So, this last topic, and this will drive you a little crazy at first, but we'll make it better. This is a duration effect when you're doing single load work. And so notice, down here, your x-axis is not intensity, it's not percent VO2 max. It's time at one workload. Also, notice you have to have certain preconditions for this to happen. The intensity of the work has to be low enough that you can cover it with mostly fat metabolism. And then the initial fuel mix has to at least have some carbohydrate. If you start an exercise, let's say just for practice of what you learned last time, if you started a workout not having eaten for the last 12 hours, what would your R value be? It would be fat, 0.7, and it wouldn't shift anywhere. But if you've had a mixed breakfast, I had pancakes this morning. I don't know where I got the energy to make pancakes, but it's wonderful. If you have had a mixed meal, and so you start the exercise, the way this is drawn out, something like 80% carbohydrate. Oh, the RER tells you, the RER here is 0.92. When you solve your math, that tells you it's about 80% carbohydrate and about 20% fat. And it's light work. Now, as you go on through time, this is like going for a long hike, going for a 3-hour hike, 6-mile hike. Notice that the amount of carbohydrate you're using falls off, and the amount of fat that you're using goes up and up and up. All right? So this is a little item compared to a lot of people go crazy at this point because they say, wait a minute, you just showed us a graph that said that fat use goes down, and there's a crossover point, and carbohydrate use goes up. What's the difference between these two graphs? The x-axis. This is intensity, and it's true. By the way, this single figure is like 90% of all exercise metabolism. To realize that the harder the rate of work, in other words, the higher the rate of ATP replacement, the more you're obligated to use carbohydrate. This is a giant principle. This thing that I'm showing you at the very end, it's why I put it off until the very end. It's sort of a little tiny cul-de-sac that is somewhat important if you're a long distance person, but it's got so many preconditions on it. You have to have had carbohydrate within 4 hours before you start. The workload has to be low enough that you can shift. I think it's interesting, the reason I'm telling you about this is it's another example of glycogen or glucose sparing. that when the body has an option, it will almost always do a shift that causes you to not use up your glycogen quickly, because it's your premier fuel for the high intensity work, and you don't know when high intensity work is going to arrive. So if you can spare glycogen, you do. And I'm going to talk a little bit then about this phenomenon. You can go insane if you want. And many people call that the Randall phenomenon or the Randall theory. I like the Randall phenomenon. It's absolutely clear that that happens. I could take any one of you, put you on the treadmill, make sure the workload is low, get an oxygen consumption measurement going on, and we could watch your R value fall half hour by half hour. It's very reliable. Randall tried to explain the phenomenon back in the 50s, and some of his theories turned out not to be quite right, but the phenomenon is true. It's true that in sustained low-intensity work, you'll progressively shift towards mitochondrial use of fat. So let's see if we can figure this out. If you have, and one way to think about this, you guys, is that if these are free fatty acids, and these are carbohydrate, there's almost like a mutual shutoff. That if glucose metabolism is proceeding very, very quickly, I think we talked about this last time, there's several ways that free fatty acid oxidation is retarded. The same is true if plentiful fatty acids are pouring into the cell, you can shut down the use of glucose, right? And it all depends on, so intensity will tend to cause you to predominate glucose. So catecholamines, epinephrine, those things will sort of push you in this, and rate of ATP replacement will cause that to dominate. And we're about to discover in low intensity sustained work, how does the muscle cell get the signal that it would be better off using fatty acid? So the first is, when acetyl-CoA and reduced coenzymes are very high in the mitochondria, well, that would be the case if you're doing a lot of beta oxidation. You're going to have a lot of NADH around, and a lot of acetyl-CoA being cut off by, snipped off the long fatty acid by the beta oxidation. That of itself will suppress the import enzyme, the gateway enzyme, pyruvate dehydrogenase. So the very products of beta oxidation will ultimately suppress pyruvate. Then this one was what Randall made in the original hypothesis, discovered in vitro in a test tube. If you put a lot of citrate in the mix, remember citrate should generally be an intramitochondrial moiety chemical. If you put citrate in the cytosol at a fairly high level, you can suppress pyruvate phosphofructokinase, right? The problem is the levels that you put in the test tube are not the same as the levels you see in vivo. They're a little too high. So I leave this as sort of a question mark. Maybe that happens. But most people are fairly certain it has to do with this. That when lots of beta oxidation is going on and providing a plentiful source of electron transport, reduced coenzymes, you automatically start to shut down pyruvate dehydrogenase. I believe this is a May. We'll leave that on the table as a May. Yeah, very good. So when energy need is low enough to be met with abundant fat oxidation, you automatically begin to shut down pyruvate dehydrogenase and favor fat import. Is that all okay? Makes sense? I don't know if you can see, I hike a lot, so it's very obvious at the end of a long day of hiking, you can almost smell your partner's breath has shifted towards, and of course I've done lots of, in the lab, monitoring oxygen consumption runs, and it's just reliable. You can watch the people shift over to fat metabolism beyond the first hour. It just keeps going. Is that all okay? Again, that's a minor point. Moses, yeah?
When you keep saying that you can smell their breath, is that because they're going like...
Yeah, they get slightly ketonic. So there's a little bit of ketone body beginning to be evolved, and ketones vaporize. Anyone smell? Oh yeah, you smell it
like acid.
who are drunk. You can smell the alcohol coming out in their breath. The ketones are a little more subtle version of that. But yeah, it smells kind of like a solvent, like acetone, kind of fruity, people describe it. Pretty mild. Diabetics do it too. So that was the end of lecture 17, and there's 3 summary slides. They all say the same thing, so you just look at the one you like the most of the 3, trying to appreciate your individual learning styles. But this, again, Elisa, this sort of goes over what your email talked to me about. Right? So, summary of everything we just said, with the last point that we just made down here, that if you're doing long duration, low intensity exercise, shift towards fat, that spares the glycogen in case there's some later high intensity work. That make sense? So again, one of the big principles throughout metabolism when you're talking about exercise is you don't want to burn through your premier high intensity fuel unless you're doing high intensity work. You would like to reserve it for the special times. So here's another summary statement, and then there's another summary statement. We are officially done. For those of you who are tired of exercise metabolism, we are now officially done with exercise metabolism. Welcome. There is a class, an MPB course. I think it may be EXB. EXB 110 is exercise metabolism. So for those of you, it's taught by Dr. Gomes. Is it in spring, Sharon, do you think?
I'm taking it here
Oh, good. Yeah. You're taking it this year?
later.
Oh, good. Good. So this is a really nice prep course for that. And anyone who's had BIS 103 is also well prepared. So if you like, I mean, I don't know what chokes you and what doesn't. This was hard for me when I first got exposed to it. But if you like it, another class taught by Dr. Gomes in the spring. All right. But that's you guys have really had what, almost 2.5 weeks of metabolism, which I think is very generous for a basic course. You have the basic principles laid out. That's pretty. So where we're going to go to next, so you needed to know all this stuff in order that we can start to talk about adaptation. I mean, for me, and adaptation, of course, for athletes is being trained. It's the fitness state. It's a phenotypic alteration such that one comes predisposed to better perform and fatigue less in the tasks of one sport, right? And so we're going to talk in great detail about that for a lot of the rest of the quarter, and specifically talk about the way that muscle cells adapt for the next 4 lectures. And then we'll talk about how the cardiovascular system adapts. We'll talk about oxygen transport in the lung. We'll just talk about a lot of stuff. So, we're now going to begin to talk about adaptations and training. And there'll be a lot of, whenever I can point out a training hint, for instance, in the last set of lectures, I pointed out that if you're going to go for more than an hour, dropping some glucose into your mouth is a useful thing to do, and you kind of want to wait until beyond 30 minutes, 45 minutes, because you want to establish the internal state that will pipe that glucose to your muscle. As I said, putting it in advance, great, now you're piping it into your fat, and you got to turn all that off, so it backfires. Again, the Gatorade people who say pre, during, and post, okay, during and post makes sense. Pre is just a marketing thing. They just want to sell more Gatorade. So, we're going to talk a little bit about adaptation. Let's see. Muscle adaptation, morphological, biochemical, and molecular variables. They alter their functional attributes in the motor units that are recruited. So one of the biggest preconditions here is, for instance, let's look at, we seem to have a spinal cord and 2 somi. There is an alpha-1 motor neuron going to 2, that's obviously condensed. Large fibers, so if we're having to guess, we are thinking that's probably a fast-twitch motor fiber because of the size of the cells. And this, it's actually made that. Why can't anyone make a figure? It's not that hard. The little skinny, this should be skinny, attaching to multiple small fibers, and then they should have added some more large muscle fibers and put the fat one on that. They've got this wired backwards. like to show my middle finger to the figure. Anyway, the point is, let's say you're doing low intensity work that only requires the recruitment of this smaller motor unit. These cells never adapt because they never turn on. And it's interesting when you think about it, I'll show you a figure in just a moment, but if you're walking casually around campus, you've probably activated something like 10% of the muscle mass in the muscles of walking. It's very small. So 90% of the muscle is just getting a massage. It's completely relaxed and sort of going along, oh, this is cool. So, gotta have activation in a cell before it can adapt. Once you activate a cell, there's a whole bunch of patterns that commonly occur. Let's see. Each contractile task has specific stresses. For instance, if you lift weights heavily, the amount of force, your peak tension, you may run out of that and the bar lands on your throat at some point. The rate of force generation, so velocity or power, one of the limiting features, if anyone's been watching the World Series, one of the hard things about batting, it's not force. The bat doesn't weigh much. The problem is speed because of the 90+ mile-an-hour ball and getting your bat to be at the right place before the ball's passed. That's a velocity issue. And then metabolic support. If and only if the same contractile task is repeated day by day, week by week, the cells will undergo highly specific adaptations. The kind of contractile pattern, I just mentioned some, long-term endurance, high-intensity resistance, speed, ballistic, we talk about throwing limbs. And then frequency, intensity, and duration. Frequency is usually sessions per week. Intensity, what fraction of your maximal abilities, whether it's 1 rep max or if you go 2 max, whatever the ability is. And duration, meaning how long is each work bout sustained. You realize, I think, that this is all overview to the adaptive process, that the genotype, the order of adenine and guanine, cytosine and adenosine, is that them? Those orders are fixed unless you've been exposed to horrible mutagens. For you, those orders in your genome are fixed, but the expression of the genes can vary. You could make 10 ATP, you could make 10 myosin and actin sarcomeres, or you could make 100. And often it's the expression of the underlying genome that is being altered in these adaptational states. What happens if you change protein expression is the phenotype, whether at the microscopic level or the whole body level, starts to change. Does that make sense? Okay. So going back to the very first lecture we had in this class, I think I told you, that lecture reviews the entire course. So sometimes you can't even understand a figure until halfway through the course. The regulation of gene expression by contractile activity. This is the oldest before and after photograph I can find. The problem was to find a photograph and a reasonable result. It's from 1904, so it's 112 years old. The gentleman used the Des Bonnet method. We didn't have systematic iron weights back then. He lifted dumbbells and bowling pins and medicine balls and juggled them and things. I think it's quite a nice result. You tracking it? So one of my questions for you would be, if you were to measure his right arm here, measure, say, diameter or cross-sectional area, and then you measure over here, or if you could measure his isolated deltoid, they're bigger. Okay, what's in them that's filling up more space? Sarcomeres. Each myofibril has added sarcomeres. There may even be more myofibrils. What are myofibrils made of? Sarcomeres. What are sarcomeres made of? Actin and myosin. There's clearly been an enhancement of the expression of the sarcomeric proteins. Right? So it's actually visible in some characteristics. So muscle is so changeable, so plastic, as we say, so adaptable, that
it's almost easier to make a list of the things that won't change, because the things that change, there's just so many of them.
So the things that won't change, the wiring doesn't change. You will never, unless there's severe pathology, you'll never have a motor neuron suddenly decide to rewire onto some new muscle cell. That's going to be stable unless you have severe neuromuscular disease. The velocity of the axon propagation, of the axon potential propagation down the axon, the characteristics of the neuromuscular junction, all that stuff's pretty well fixed. And it's by the way, it's faster than anything that we can voluntarily do. It's over-engineered. So we don't have to really worry about that. The genotype doesn't change. Sometimes when I talk about changing gene expression, people get confused and think that, you mean exercise mutates me? It's an X-Men thing. No. We saw that some proteins are, terminally differentiated. Just like the hemoglobin you have in your eye color and your iris are sort of terminally differentiated. We saw that the isoform of the ATPase on the myosin heavy chain, that's pretty much fixed in each cell by the time you're born. You could be a hybrid. One cell may have all three isoforms, but for each cell that's formed, it's pretty well a fixed condition, and it's not going to alter. And then I think I mentioned this, that in human adults, during childhood, we add sarcomeres end on end all the time because our skeleton keeps getting longer and the muscles need to be attached to either end of the bone. So if your femur, when I arrived, my femur could not have been bigger than this. And now it's this big. Clearly, during growth and development, I added a lot of sarcomeres end on end. Once we reach adulthood, that pretty much stops. It's hard to get a stretch on a muscle big enough and hold it long enough to add end on end sarcomeres. Yes?
Is this why we add parallelism?
Yeah, parallel is much more plastic in an adult than series. It's funny, Mary, the ability is still in there. My father was an orthopedic surgeon, and occasionally you actually do a limb lengthening surgery. Someone's had a poliomyelitis, and this limb is 4 inches shorter than that one. You go in, cut the femur in half, and slowly step it out, right? And that adult will actually add in series. But you see how it's a pathological intervention. It's not natural, but it's in there. The capacity to do it. You can also do it in some animals that have fixed postural muscles, like a chicken. The patagialis is the muscle that holds the chicken wing in. If you forcibly pull the wing out and then put like a toilet paper tube over it so it can't shorten, the chicken is now doing yoga 24 hours a day in that one muscle. It's under huge stretch. Dr. Hawley did this experiment here on the campus to get his PhD and discovered that an adult chicken will happily add sarcomeres end on end, but you have to put a 24-hour-a-day big stretch on it. Let's see, what else is on here? Maximum contraction velocity. Can you guys see how this won't change? Because I just told you that you can't change your myosin ATPase, and as an adult you can't add series. See how these add up to maximum speed? So maximum speed of shortening will not change in your adult. Everything else changes. And I threw on just some of my favorites. Side-by-side sarcomeres, Mary. The total area of myofibrils. The concentration of the enzymes in the cytosol, like lactate dehydrogenase or phosphofructokinase. The total number of mitochondria. The density of mitochondria within each cell. The density of the enzymes of oxidation within the mitochondria. The relative proportion of enzymes, meaning that if someone is doing an anaerobic sprint training, they will preferentially add cytosolic enzymes. If someone is doing long distance oxidative training, it will preferentially add mitochondria to mitochondrial enzymes. And there are changes in the connective proteins, but we're just starting to study those. Dr. Barr has about 4 studies going on right now about alterations in the